Thank you for attending this presentation. My name is KeivanR.wmv, a graduate student at the Department of Civil and Environmental Engineering at Rice University, and I'm doing this research with my advisor, Dr. Duanis Osorio. I'm going to talk about topological bounds for reliability assessment of large lifeline systems, with emphasis being put on power transmission grid. The power transmission grid functions as the backbone of the modern societies. Almost 40% of total energy consumption nowadays is in form of electricity. The power transmission grid is also very interdependent with other lifeline systems such as transportation, water and gas distribution, and communication network. Is such an important network reliable enough to address our needs? Well, it's getting less reliable as the gap between demand and what it offers widens. Today, it's being operated at a larger capacity compared to a couple of decades ago. The demand for quality service has increased and the grid has not been able to keep pace. The network still uses technology from the 1960s along with more modern instruments. The network has been growing unplanned for the most part. It consists of small regional grids just joined together to establish the current formation. Estimates show that blackouts and power cuts cost the United States of America around $80 billion annually. There are a few established ways to improve the reliability of the network. You can introduce more green sources such as wind or solar energy. You can invest in building more transmission lines and improve the connectedness of the grid. Or you can move towards the idea of smart grid, where you can have data transmitted over the power lines and have modern control technology among other interesting features. In this research, however, we're going to show how a better understanding of the network structure by looking at its topology can help improve its reliability. The scope of this research is to explore the topological features and spatial distribution of power transmission structure and investigate its performance under natural hazards or deliberate attacks. We introduce bounds on the performance of the power transmission systems by looking at their topology. The approach we're adopting in this study is looking at all possible failure scenarios. In today's state of the practice in power transmission industry, the procedure known as N-1 is usually followed, where only single components in a system can fail. However, looking at all possible failures where any number of sets consisting of any number of system components can fail leads to a combinatorial problem. Such K out of M problem is very computational demanding, and calculations just grow exponentially with the size of the network. There are two network models that are extensively used in network topology studies and are shown at the right hand side of the screen. At the top, there is the minimum spanning tree, that is the minimally connected formation of a graph. The number of the links in a minimum spanning tree are just enough to ensure that the network is connected. Therefore, removing any number of links leaves disconnected nodes. At the bottom, there is the greedy triangulation formation that has the maximum number of links in a planar graph. It's quite obvious that the greedy triangulation formation is much more resilient to attacks compared to minimum spanning tree due to its being more connected. In the center, you can see the IEEE 118 node test network. Each node is either a generator or a substation for transmission. The network has a complex structure in the sense that it cannot be reduced into sets of series or parallel nodes. However, the topological characteristics of this network fall in between those of its extreme model. This is verified by a statistical analysis on the topological features of real transmission networks. Here, the transmission grid of Harris County in Texas is being compared to its two model networks with the same number of nodes. The real network comes in between the models in every of these 5 well-known topological features, so we may say that the minimum spanning tree and greedy triangulation are indeed bounds on the topology of real transmission networks. The metric that is being used in this research to evaluate the performance of the network in failure scenarios is the connectivity loss. Connectivity loss is a simple and yet meaningful metric to evaluate the state of the system after perturbation. It is basically the ratio of the average number of generators still connected to substations to the original number of such generators. Connectivity loss provides more insight about the state of the system than simply counting the number of disconnected nodes. Yet, it is simple enough to be included in our combinatorial analysis of failure scenarios. For this study, we're looking at 10 transmission networks in the states of Texas and California. Texas has its mostly independent network known as the Texas Interconnections. 6 populated areas have been chosen for this study. There are Harris County, including the city of Houston, Dallas, San Antonio, Austin, El Paso, and Brownsville. California is part of the Western Interconnections and one of the largest consumers in the country. The 4 chosen networks here are Los Angeles, Sacramento, San Francisco, and San Diego. Doing the combinatorial K out of N calculations for real large networks can take from several weeks to a few months to complete even on the fastest computers. This is because we are accounting for every possible failure scenario, so any number of components in the network in any order can fail. To accelerate the calculations, we have applied the center limit theorem to choose a set of representative samples for each scenario. For example, you may have millions of ways of removing 60% of nodes in an 800-node network. But since you will have a normal distribution of the means, the mean connectivity loss you calculate for 400 of them can represent the mean for all of those scenarios. Here, the connectivity loss curve for Los Angeles network with more than 1,000 nodes is shown along with the standard deviations of the calculations. Even though we're using sampling, the connectivity loss calculations for a network of this size still runs for up to a week on a computer cluster with parallel computing. The standard deviation curve shows the accuracy of connectivity loss estimates at each ratio of the removed nodes. The performance of a power grid system under perturbation is compared to that of its model networks in this figure. Here, the connectivity loss curve of Los Angeles actually falls in between the curves of the minimum spanning tree and the greedy triangulation with the same number of nodes. The greedy triangulation is more resilient than the real network, which in turn shows more resilience compared to the minimum spanning tree. Here, the connectivity loss curves are shown for all 10 networks under study. The interesting fact is that for all cases, the model networks that are defined as extreme bounds on topology of a network also introduce bounds on its performance. In all 10 cases, the connectivity loss curves of the network falls in between those of its model networks. Another interesting fact is the bilinear form of the connectivity loss curves. In this figure, that is for the network of Dallas, curves are estimated by 2 lines for the network itself as well as its 2 model networks. The bilinear form can be exploited to reduce the computational demand of calculations, since calculating the extreme left and extreme right regions of the curve seems to be enough for a quick estimate on the behavior of the transmission grid. So for conclusions, introducing bounds on the performance of a system can help for a quick evaluation of its behavior under threats. Topological models, minimum spanning tree, and greedy triangulation not only define extreme topological features, but function as the performance bounds for the transmission networks. The bilinear form of the connectivity loss curves can help significantly reduce the computational demand for our calculations. I want to thank you for taking time to attend this presentation. I also want to thank the National Science Foundation for funding this research. Please leave your comments below this video or send them directly to me at this email. Have a very nice day.